We are ready. Yeah, thank you. I would like to welcome you to the 20th lecture in the Cloud Physics lecture series conducted by IITM Pune. And today's lecture is delivered by Dr. Vaughan Phillips. And let me invite Dr. Mahen Konwar from IITM to introduce Dr. Phillips. Thank you.
Yeah, thank you. Yeah, welcome, Dr. Phillips. It's my great pleasure to introduce Dr. Vaughan Phillips. Dr. Phillips is a senior lecturer at LUND University in Sweden and does research about cloud physics from a modeling perspective. By creating new schemes to treat ice and droplet initiation by various pathways, for example, primary and secondary ice production, and to represent other processes such as ice morphology, sticking efficiencies in ice-ice collisions, time-dependent freezing and melting. He studies how the environment controls cloud properties. Recent interests are bioaerosols, impact on clouds, lab field experiments to observe fragmentation of ice, and use of artificial intelligence to represent clouds in global models. So with this, I welcome Dr. Philip to deliver his talk.
Okay. Okay. Thank you, Tara and Mahen, for the introduction. And it's a privilege to be here today to talk, to give this lecture about my new theory of cloud microphysics. So I'll just share my PowerPoint. Okay. So today I will talk about a theory I've published recently about in-cloud activation and microphysical quasi-equilibrium during deep ascent. I think theory is important in science because this allows causation to be studied without all the complexities of reality. So in this talk, I'll show how a theoretical model can be created so as to target a particular set of processes, so as to understand causation. The theory aims to drastically simplify cloud microphysics so as to create analytical formulae that can let us elucidate causation. So first of all, I will delineate some basic concepts of what is in-cloud activation, for example, and I will outline the dilemma and my approach to solving the problem. Then I'll describe my theory. And the theory has three state variables, and I look at the equilibria of the theory for those three variables. Then I show some applications of those equilibria. Then I move on to the trajectory in the phase space for a standard case of applying this theory. And I show some results from feedback analysis about the stability in the phase space. And then finally, I wrap up with one or two sensitivity tests. So I hope people can hear me clearly.
Yes.
Good, good. So the clouds seem to be quite ephemeral, and and inspirational. Clouds have many colors depending on whether it's sunset or the middle of the day, depending on the weather. Clouds must have existed on Earth for as long as the oceans have existed, for more than 3 billion years. For as long as the oceans have existed, there's always been evaporation, and therefore there's always been precipitation from clouds. So the atmosphere has always had a decrease of the temperature with increasing height, and so ascent has always been necessary to mostly to create clouds. It's the ascent that brings air to saturation by creating cooling. And inside clouds, ascent has always been the source of supersaturation that organizes the various microphysical processes. So specifically, ascent determines the supersaturation, which determines conversion of aerosol particles to droplets. Every cloud is a vast number of aerosols that have become visible by virtue of activating to become cloud droplets. So every cloud is a subset, a visible subset of the aerosol population. And the supersaturation also controls conversion of solid aerosol material to ice crystals in clouds that are cold. The supersaturation controls diffusional growth in clouds. So the cloud particles making up any clouds get their mass from condensation onto the condensate or vapor growth of ice. And this in turn determines the intensity of precipitation. So clouds that have fast ascent, such as convective clouds, have fast rates of precipitation, and vice versa for stratiform clouds with weak precipitation. Clouds in the mixed phase region of temperature between 0 and minus 36 Celsius can either be mixed phase with liquids and ice, or they can be ice only. And the ascent is the razor, so to speak, that separates ice only and mixed phase clouds. So this is a simple evolution equation for the supersaturation in an adiabatic parcel for a liquid-only condition. The evolution of supersaturation has a source from ascent, and it has a sink from condensation onto the cloud droplets. You see the condensation term, I hope you can, the condensation term is proportional to the supersaturation. And so at long times, the supersaturation is approximately at equilibrium, and the equilibrium is just omega divided by eta. Omega is proportional to the ascent, eta is proportional to the droplet number concentration, and also I think the mean droplet size. And we'll come back to this. So every cloud that has cloud droplets has production of cloud droplets near cloud base. And this is what cloud base looks like. The exact cloud base is at 0 supersaturation. The supersaturation is the fractional excess of the vapor pressure above water saturation. You see that about 10 or 20 meters above cloud base, there's a peak in the supersaturation, and that's created by the swelling up of droplets that are initiated in the first 10 or 20 meters of ascent. So the condensational growth provides a sink of supersaturation. And so the supersaturation overshoots equilibrium, then decreases towards equilibrium. So if we look carefully at what happens to the aerosol size distribution, you see that the environmental aerosol size distribution schematically looks a bit like this blue line here. When the parcel rises to the peak of supersaturation, the aerosol size distribution is chopped like this. It loses all the aerosols, which convert to cloud droplets larger than this critical size. So for any given aerosol generally, the larger the dry size of the aerosol, the smaller the critical supersaturation at which it converts to become a cloud droplet. So, so during this initial ascent at cloud base, first the largest aerosols convert, and then smaller and smaller aerosols convert until we get to this orange dashed line here. And then the activation stops at the supersaturation maximum. So while the supersaturation is less than this maximum of supersaturation, there is no more activation of aerosols. And consequently, we have a constant droplet concentration with height. So hypothetically, you can see that if somehow the supersaturation were to become big again during distant ascent, if it were to exceed this peak value at cloud base, then we would have continuation of the aerosol activation. Aerosols in this orange size distribution would convert to become cloud droplets. And we call that in-cloud droplet activation. So in-cloud droplet activation was discovered by Harry Ox in 1978. So he performed detailed simulations with a bin microphysics model of liquid-only cloud. Many sizes of cloud droplets were represented explicitly with bins. The updraft speed was constant, and in this simulation, he assumes there's a maritime aerosol profile, and there's a maritime CCN activity spectrum. So you see, this is time since leaving the initial position. You see the maximum at cloud base. Here is cloud base, and you see that after cloud base, after this peak is left, the cloud droplet concentration is almost constant. It doesn't increase. You see here, he predicts the radar reflectivity in his model, which is dominated by the precipitation. So during a lengthy ascent, over about 10 minutes, the precipitation intensifies, and as a consequence, the cloud droplet number declines almost exponentially, in fact, towards zero. And when the cloud droplet number declines, the equilibrium supersaturation that we were talking about earlier, here, it must increase. So eta is proportional to the droplet number. And so the supersaturation increases, and we have in-cloud droplet activation. What's interesting here is that the droplet number is almost at equilibrium. So there's a balance between production of new droplets by in-cloud activation and the depletion of the droplets by accretion onto the precipitation. And so this equilibrium makes one wonder whether there are negative feedbacks or perhaps positive feedbacks at work. So the hypothesis I have is that any cloud in a microphysical sense can be viewed as a system of positive and negative feedbacks that unify all the microphysical species as one system. So you can view a cloud as a system of feedback processes. And so to tackle this hypothesis, I create a theory that involves some drastic simplifications. And I want to focus on in-cloud droplet activation in particular. I assume there's vertical acceleration that is driving an increase with height of the supersaturation. So for decades, aircraft observations through a given cloud have revealed that the ascent increases almost linearly with height, because in a cloud, the buoyancy is fueled by latent heat release, and that the buoyancy causes an increase of the ascent with height. I assume that the hydrometeors are all a single phase, so either liquid or ice, but not both. And to be honest, I don't really like entrainment. So with that confession, I keep the parcel adiabatic. But if we want to, we can come back to this in future and include effects from entrainment. So here is the parcel. There are 3 state variables in the parcel. There are cloud particles and there are precipitation particles. The cloud particles are described by a total mass mixing ratio and a total number. This is the total mass of cloud particles per kilogram of air and the total number of cloud particles per kilogram of air. The precipitation is described only by the total mass of precipitation per kilogram of air. The tilde, you see on each symbol I have a tilde symbol, and that means that the variable is dimensionless. And the dimensional ordinary variables are without a tilde. So dimensionless time is just the time divided by a reference time scale, which is about 3 minutes. And this variable C3 is a coefficient for accretion of cloud particles by precipitation. So if we look first of all at the mass fields, these are the evolution equations. The rate of change following the motion of the parcel of the cloud mass has a source from condensation and a sink from accretion. And similarly, the rate of change of precipitation mass following the motion of the parcel, which is only upwards, has a source from accretion of cloud and a sink from sedimentation. And you see that the sedimentation term is a little bit complicated relatively. There's this exponent beta. So beta is bigger than unity, somewhere between 4/3 and 2, depending on the context. The beauty of non-dimensionalizing the evolution equations is that they become quite simple. So there are no constants apart from c here and beta and phi. So this constant c, you can see, is driving the evolution of the mass fields. And I call C the condensation precipitation efficiency. So there's this constant C3 I just mentioned, and there's also C0, which is the true mass condensation rate. C0 is the ascent times some exponential function of temperature. I think it's the rate of change of the saturation mixing ratio with respect to temperature, which is a function of temperature. And thirdly, the evolution of cloud particle number follows this equation. So I assume that for the purposes of treating in-cloud activation and the supersaturation, there is a constant rate of increase of ascent with height. And that is proportional to W here. W is a dimensionless measure of the vertical gradient of the ascent. A is related to the CCN concentration, or the aerosol loading. And you see that n tilde is the dimensionless cloud particle number, which is just the true particle number divided by the normalized aerosol, normalized CCN concentration. So I assume a power law CCN activity spectrum, the number of clouds, particles activated, equals C1 times the supersaturation to the power of little k. So, so I call F here an in-cloud activation efficiency. It represents the source of droplet number from in-cloud activation. And the sink on the right-hand side is accretion onto precipitation. So we have three evolution equations with three unknowns. And so we can solve these numerically. Sometimes we can solve them analytically. So now we can set the time derivatives on the left-hand side of those three evolution equations to 0, and we get the formulae for the equilibria. So for the mass, we have these two formulae. So remember that the two evolution equations for mass form a closed system. So the two mass variables here are driving the system, and the cloud particle number is a passive passenger, if you will. By the way, I should say that one of the drastic simplifications I've made to create the evolution equations for mass is to neglect what's called autoconversion. So, the first precipitation embryos that form are formed by collisions between cloud particles. And I assume that most of the time once the precipitation has started, the conversion of cloud mass to precipitation mass is dominated by accretion of the one by the other. So I assume autoconversion can be neglected almost all the time. And I also assume autoconversion functions just like a digital switch. So when cloud droplets become supercritical, larger than 20 microns in size, then there's a pulse of precipitation. And once that signal's received, then the accretion takes over. So when I solve these two equations numerically, I provide a tiny pulse for a tiny amount of time to convert a small amount of cloud mass to precipitation mass, and then I forget about autoconversion altogether. So the equilibria for the mass of cloud condensate increases with C, and similarly for precipitation mass. So you see that the equilibrium cloud mass is inversely proportional to the precipitation mass, and the constant is just C. So if we're interested in the contrast between stratiform clouds and convective clouds, then we choose a value of beta of about 2. So omega is just 1 divided by beta. And then we get the nice result that both equilibrium masses are proportional to the square root of the ascent. And this sort of tallies with what we know from aircraft observations and from numerical modeling of cloud systems. So the ascent differs by a factor of about 100 between stratiform clouds and convective clouds. Convective clouds, by definition, have ascent of up to roughly 10 meters per second. Stratiform clouds have ascent of up to roughly 10 centimeters per second. There's something like an order of magnitude difference between the liquid water contents of stratiform and convective clouds. So the theory seems to tally with what we know, both from models and from aircraft observations. And for the cloud particle number, again, there's an equilibrium. The equilibrium involves balance between in-cloud activation and loss from accretion of cloud droplets onto precipitation, whereas for the mass fields, there's a balance between condensation for the cloud and accretion onto precipitation, or a balance between accretion for precipitation and sedimentation. So there are different reasons for the equilibrium for each variable. And you see for the equilibrium number, here's our in-cloud activation efficiency F, and here's the equilibrium precipitation. So we have the source divided by the sink, roughly. And when we turn the handle and write this out in dimensional terms, we see that the equilibrium cloud particle number increases roughly with the square root of the CCN concentration, the aerosol concentration, and with some higher power of the Ascent, roughly. So if dW by dz scales with W, then the droplet concentration is roughly proportional to W to the power 1.5, something like that. So there's a modest sensitivity to aerosol conditions and a strong sensitivity to the thermodynamical state of the cloud. We can say if the cloud mass is somewhere near equilibrium, then the fraction of cloud droplets that are from in-cloud activation must approach unity in a sort of asymptotic exponential fashion on a time scale of QP. So this fraction increases on a time scale of several minutes. And so very soon during ascent, almost all the cloud droplets are from in-cloud activation, soon after in-cloud activation has started. So I'll show some numerical integrations of the evolution equations for a standard case. The standard case is a slightly continental convective cloud with ascent of about 5 meters per second, with 1 meter per second per kilometer of vertical acceleration for the purposes of treating the in-cloud activation. And so this is the phase space of the mass fields. So this axis here is cloud mass, and this axis here is precipitation mass. The black line here is the neutral line. So initially the system starts here. The system initially has 0 precipitation, and this is an unstable equilibrium. When the cloud droplets size, mean size, exceeds some threshold of about 20 microns, I apply the instantaneous pulse to create a small amount of precipitation so as to represent implicitly the effects from autoconversion. And then I forget about autoconversion, and the system then moves along this trajectory here, and it approaches the equilibrium. So you see the equilibrium point is an attractor. The attractor is reached by a sort of spiral. There's an orbit that becomes ever closer to the equilibrium point. I think without ever actually getting there, but exactly. The feedback analysis works by linearizing the evolution equations for a perturbation, and we define eta as the fractional rate of change of the perturbation of mass or perturbation of cloud particle number. So the formula, which I won't show here, has a solution for 0 eta, and that's the neutral line shown in black here. So we have a region of instability where positive feedbacks prevail for the mass, where eta is positive, and a region of stability where it's negative. So you see here the first equilibrium is unstable and the final equilibrium is stable. So it's interesting that when we look at clouds in our everyday lives, sometimes we see clouds do things very suddenly, such as producing rain. Rain, it's a common experience that when it rains, the rain arrives very suddenly if it's a convective cloud. And I think this is a visible manifestation of the instability of the initial equilibrium. And philosophically, one can ask, why does the system exist at equilibrium for most of the time? And I think the reason is that when the system is initially in the unstable regime, the system moves, the system explodes very quickly and is literally thrown out of the instability regime. And so it just, by default almost, it ends up in the stability regime. And so that's why the system ends up at this stable equilibrium. So for droplet number, we have no change of the droplet number while there's no precipitation. And then when precipitation starts, there's unstable collapse of the droplet number. But very soon, there's a region of stability where there's an equilibrium. So again, there's a neutral line for cloud particle number. So the theory can help us understand the chain of causation that creates the stability of these equilibria. So if we have a fluctuation, a positive fluctuation of precipitation mass, this will lead to a negative fluctuation of cloud mass by more accretion, which then produces less precipitation, which then opposes the original fluctuation. So there's a negative feedback at work in the stable regime. And for cloud particle number, again, there's a chain of causation creating a negative feedback. If we have a positive fluctuation of more cloud particle number from in-cloud activation, there's more droplets to be accreted onto precipitation, and there's a slower rise of the supersaturation because there's a stronger condensational sink. And then there's less in-cloud activation, fewer cloud particles, and the original fluctuation is opposed. So one can draw similar cartoons for the positive feedbacks as well in the unstable regimes. So here's an example of a CCN sensitivity test. So in the control run, we had a sort of a slightly continental aerosol condition. So now we increase and decrease the normalized CCN concentration by a factor of 10. So this alters the equilibria of cloud droplet number. And you see that for each new aerosol scenario, there's a different neutral line. But in each case, the equilibrium is fairly close to the neutral line on the stable side of the neutral line. So for me personally, it's quite satisfying to see these plots in color It's so much easier to read. Often when one publishes plots in a paper, one has to choose black and white just to minimize costs. It's nice to see green and red. So here on the left are the mass fields. Now, as we already noted, the equilibria of mass have no dependence on the droplet number or on the aerosol condition. So in all cases, we end up at the same equilibrium. You see that the timing of the initial pulse to kickstart the precipitation increases with the aerosol loading. So in the polluted case, the droplets are smaller, and so there has to be more ascent until the droplets reach the critical size of 20 microns for precipitation to start. In the polluted case, we have much wider swings of mass in the approach to equilibrium. It's interesting that the final state of the mass field is rather insensitive to aerosol loading. And so one can infer that aerosol conditions, insofar as they affect clouds, must be a higher order effect compared to the thermodynamic effects on cloud properties through the ascent. So here's a timeline of cloud particle number. The thick line is the total cloud particle number, and the thin lines are the components from in-cloud activation. You see that as soon as the precipitation starts, there's a collapse to the new equilibrium of number. And almost as soon as the new equilibrium is reached, as we've been saying, almost all of the cloud particles are from in-cloud activation, or some people call it secondary droplet activation. And here on the right is the timeline of mass fields. So you see how the polluted aerosol conditions create a delay in the onset of the precipitation. So I think the thick line is the precipitation and the thin line is the cloud mass in each case. But what's quite interesting is that even though the polluted case is delayed in the onset of the precipitation, I think partly because the extremes, the overshoot in the polluted case is much more exaggerated, there's a faster approach to equilibrium. So the polluted case catches up with the other cases fairly quickly. So in all cases, we arrive at equilibrium in a dimensionless time of less than about 8. But in the control case, in the standard case, we get there in a dimensionless time of about 5 or 6. So the reference time scale is 200 seconds, so 5 or so that's about 1,000 seconds, 15 minutes. So to put that in perspective, the ascent is about 5 meters per second in the standard case. At about 6 kilometers, at about 5 kilometers above cloud base. And in this simulation, the parcel is rising from Cloudbase at a fixed rate of ascent. So I use what's called a distorted physics approach, where for the purpose of treating condensation, I assume a constant rate of ascent, and for the purpose of treating the in-cloud activation and the supersaturation, I assume a constant vertical gradient of the ascent. So I call this a distorted physics approach. But this is necessary to fix the equilibria so as to create some understanding of the system, so by simplification. So these are my conclusions. So the theory explains in-cloud droplet activation as a continual prolonged phenomenon during deep accelerating ascent. And the theory shows that depletion of cloud liquid by precipitation is a fundamental cause of in-cloud droplet activation. And this involves a continually increasing supersaturation, just as Harry Ox predicted. And some scaling analysis that I haven't gone into today, but it's in the paper I published, shows that when precipitation is present, the ascent only needs to be at least twice the cloud-based value for there to be in-cloud activation, typically. And so in-cloud activation must be ubiquitous. And even in stratiform cloud, if there is any vertical acceleration of the weak stratiform ascent, then again we would expect in-cloud activation. The phase space shows that the trajectory is initially in an unstable regime where there's an explosive growth of the system. The initial onset of precipitation involves explosive growth of precipitation mass away from the initial unstable equilibrium of zero precipitation. All three variables reach quasi-equilibrium. The contrast in mass fields between convective clouds and stratiform clouds is adequately predicted by the equilibrium formulae in terms of orders of magnitude. I've not had time to show this today, but I show this in the paper that was published a couple of months ago. This theory applies also to ice-only cloud, partly because of the close physical analogy between diffusional growth onto ice and diffusional growth onto liquid. There's some interesting papers from Adam Warble and Lebeau showing that for vigorous convection, the main control is thermodynamic, and the convection is only weakly sensitive to aerosol conditions. And my theory sort of explains this in terms of the quasi-equilibria of the mass, while at the same time the cloud particle number is of course sensitive to the aerosol loading. So when convection is deep, the parcels will arrive near their quasi-equilibria anyway, fairly soon during the ascent. And I've not shown this today, but this theoretical setup resembles a full nonlinear solution for a realistic situation. So the assumptions and simplifications I've been talking about seem to be valid. So I'll finish there, and thank you for listening, and greetings from Sweden.
Thank you, Vaughan, for a wonderful talk. And I request Mahin to look at the questions from the YouTube.
Yeah, we have two questions. Actually, first is a statement from Dr. Andian Tomkin, and the second was a question. So Dr. Tomkin says processes such as autoconversion do also depend on the in-cloud droplet size distribution.
Yes. I can imagine that's true. Yes. Yeah. I mean, I based my assumption of a dependency on the mean droplet size from looking at the Kerudinoff and Kogan bin microphysics simulations for marine stratocumulus. So yes, it would be interesting to refine the theory by including some dependency of my implicit switch that I was talking about on using the relative dispersion of the droplet size distribution that you're talking about. That's a good idea.
Yeah.
Thanks for the suggestion. Yeah.
Yeah, the second question, the question is, Dr. Tomkin is asking, I was wondering how much uncertainty there is in this equation set due to the fact there is a fixed implicit assumption about in-cloud heterogeneity.
Right. So I guess if I can reframe the question, so effectively we're talking about the assumption that a single point or described by this adiabatic parcel can represent a whole cloud. Yes. I mean, one could. I mean, this is only one theory, and one could create a statistical version of this theory, where one could suppose in the cloud there is a probability distribution of vertical velocities, and one could treat the probability distribution of the cloud properties from many applications of this theory to the full continuum vertical velocity. I mean, I guess the purpose of this theory is not to provide a realistic simulation of a cloud. For some reason, I often think of a social event I went to when I was when I was a postdoc at GFDL, and present there was the great Professor George Philander, and he's a professor of oceanography. And at the social event, he said, "I think reality is greatly overrated." And I often think of Isaac Held's paper from 2005 in BAMS, where he describes two types of science. He says that there's science that aims to describe reality with as much fidelity as possible. And that can involve very detailed numerical models. And there's also science that aims at understanding. And in this philosophical article in BAMS, Isaac Held argues that the great advances in understanding in medical science, for example, have involved using a hierarchy of models with the type of science that aims at understanding. And when one aims at understanding, one has to drastically simplify, to create a theory that targets a particular process so as to understand its causation. So I guess I would reply to your question, to your point, by saying that the purpose of the model is not to provide an accurate description of reality, but rather is to arrive at some sort of understanding. So if I am able to predict the order of magnitude correctly of some of these quantities, such as liquid water content for the convective stratiform contrast, then I'm satisfied with that, because the focus is on the reasons for that.
Yeah, thank you. I think this answers his question. Madam, you have any question?
Yeah, you please take questions from the other participants here. After that.
Yeah. Anybody has any question? Yeah.
Okay. Vaughan, I have a couple of questions. One is regarding you mentioned that you are not considering the entrainment effects in your
Yes.
theory. So
I'm guilty as charged.
Yeah. Have you investigated how much of a difference your theory makes compared to a cloud that is not adiabatic? It is actually entrained. Have you made any comparison of your theory with that, or what is the actually what's the amount of liquid water content that may be depleted, or maybe?
Yeah. Yes, I mean, that's a good point. I've not done that. I mean, maybe I can share again. Maybe I can share and go back to the PowerPoint and go to the equation. I guess I can think about that now.
Yeah.
I mean, if we go right back to the beginning, you see the famous equation for the evolution of supersaturation here. This is actually derived for an adiabatic parcel. Yeah. If you look in Rogers and Yao, which takes this from a previous paper. And in fact, the equilibrium supersaturation here is actually quite a good estimate of the real supersaturation, because I think people have tested this in numerical models.
Yes.
And the reason is that the time scale for the approach to equilibrium is shorter than the time scale for dilution during ascent. So 1 over eta is a couple of seconds, whereas there'll be dilution by 10% over perhaps 1 kilometer of ascent in deep convection, perhaps roughly. But one can apply that principle here, that the time scale for approach to equilibrium of mass is perhaps several minutes. I think I estimated it in the paper. And over several minutes, there might be a kilometer of ascent, maybe, so 600 seconds times 5 is 600 seconds times 5 is 3,000, 3 kilometers. So the mass fields approach equilibrium on a height scale of 1 or 2 kilometers. So yes, you would expect some influence from dilution, but one could. So one would expect these equilibria of mass to be perhaps reduced by entrainment, but you could just include an entrainment term if you wanted to here on the right hand side. So plus E some fractional entrainment rate times Q minus 0. So minus E times Q and minus E times QP, and then those and then the E's, the entrainment rate would show up in the equilibrium expression here. So I guess it would be fairly straightforward to include entrainment effects in this theory. So that's a good point, actually.
Yeah. Actually, there are a couple of other questions also online, Mahin.
Just now.
We have missed some more questions.
Yeah, Neelam is asking, how does the vertical velocity looks for different pollution simulation?
How does the what velocity? Parcel.
Looks like for different kind of polluting environment in your simulation.
How does the parcel ascent vary with the aerosol condition? Right. While I'm sharing, just go there. Well, so the answer is simple. So I just use vertical velocity as an input parameter. So it's something prescribed, and so in my sensitivity tests, I do not alter the updraft speed. So my model here is focused only on the the chain of causation in the microphysics. But of course, in reality, there would be some invigoration of the ascent by the buildup of unaccreted cloud liquid aloft, and the change in the latent heat and latent cooling of evaporation with intensification of downdraft. So in reality, there would be some degree of invigoration of the dynamics by extra aerosols. But in the sensitivity tests, I don't treat that. There's another sensitivity test I show in the paper where I alter the updraft speed without altering anything else. So it's possible to combine the two sensitivities to estimate what aerosol induced invigoration of the dynamics would look like.
There is one more question.
Yeah.
From Ramakrishna.
Ramakrishna is asking whether evaporation is considered in the downdrafts in your simulation.
So the easy answer is no. So in this theory, I treat only ascent, and in fact, this is a good one. So here, so my theory predicts that in-cloud activation actually will not happen during descent. And so that's why my focus is on the ascent in this theory. But of course, in a real cloud where the dynamics are responding to changes in the microphysics, then yes, aerosol-induced changes in the cloud liquids, such as we see here, would yield more intense evaporative cooling, which would drive faster downdrafts. But that the whole web of dynamical effects I've neglected. So again, my strategy for creating a theory is drastic simplification, and so I forget about dynamical effects from all these microphysical changes at present.
Yeah, thank you. And there is no more question from the YouTube. Can I ask one question?
Yes.
Yeah. So have you done any kind of sensitivity studies? If you introduce some Zine CCN, then how your this in-cloud activation will be affected?
Could you say that again? Sorry. Did you say giant CCN?
Yeah, if you include or include some giant CCN in your aerosol spectrum, so how your in-cloud activation is getting changed or affected?
Yes, that's a good question. These have been some really good questions. I mean, I could maybe, if I go here, maybe, I mean, I think the chief effect of giant CCN would be to slightly hasten the onset of precipitation. and so the trajectory would start to follow this green curve here instead of the blue curve. So there would be a faster production of precipitation slightly, and that would strengthen the sink of cloud particle number, which would promote in-cloud activation, I think. Slightly, but only slightly. So here's the equation for the fraction of cloud particles that are from in-cloud activation. And you see here this C upon phi to the power omega is...
Your slide is not shared. Yeah, your slide is not shared. But yeah, we can go back and see.
Sorry. Yeah, let me just share. Sorry, I forgot. Share. Yeah, share. Okay, can you see it now? Yeah.
Yeah.
So with this equation for the fraction cloud particles that are from in-cloud activation, so you see this factor C divided by phi all to the power omega. So this is the precipitation mixing ratio. So the more precipitation there is, the faster the increase of this fraction of cloud particles that are from in-cloud activation. And so the precipitation removes cloud particle number, boosting the supersaturation. And so the presence of some giant CCN would probably slightly intensify the in-cloud activation. And I think we see that here perhaps with so in the maritime aerosol case, which kind of qualitatively mimics the presence of giant CCN, you see how the buildup of secondary droplets is promoted. So in the maritime case, there's a faster onset of precipitation. So more giant CCN would slightly promote in-cloud activation.
Yeah, thank you.
But to be honest, for other reasons, I don't think giant CCN are a very strong effect on deep convection. I think there's some published modelling studies that more or less show that.
One more question.
Thank you. Yeah, there's another question. Dr. Vishari Kanawade.
Yes.
He's asking, in-cloud droplet distribution broadens from base to top, and the entrainment or outflows can alter in-cloud droplet distribution. Any comment on outflow or entrainment or both effect?
Yeah, interesting. Yeah, I think I'm still sharing. So entrainment would reduce these equilibria of the mass fields, because the entrainment's happening on a similar timescale to the approach to equilibrium, perhaps. And the mixing of different cloudy parcels will tend to broaden the size distribution of cloud particles, and so that will promote coalescence. That will have a similar effect to reducing the aerosol load in the CCM concentration. So in-cloud mixing of different cloudy parcels with different histories would be similar in effect to going from the blue line to the green line, perhaps. And in this modelling framework, in this theoretical framework, where I consider a single parcel, of course, the outflow from the parcel to the surroundings does not affect the properties of the parcel. But of course, in reality, things that go out into the environment can be recirculated and re-entrained back into parcels lower down. So when condensate evaporates, the aerosol particles are regenerated, and those can sink in the compensating substance and be re-entrained into parcels. So one big simplification I've made in this theory is to neglect entrainment of aerosols. So in reality, if we go back to the evolution equation, so in reality, there are large aerosols continually being entrained into an updraft, and these will activate to form cloud droplets without quite possibly the supersaturation needing to be bigger than the peak value at cloud base. And so I think if I were to adapt my theory, I think that effect would be at the top of the to-do list. So I think Anne Fridland showed in her science paper in 2004, I think, that most of the cloud droplets in a deep convective updraft are from in-cloud activation, from the activation of aerosols entrained laterally from mid-levels in the clouds, from the environment. So I would have to add some extra terms to represent that in this evolution equation for cloud particle number.
Yeah.
So that's thank you for the excellent questions, and
Thank you.
This gives me plenty of ideas.
Are there any more questions, Mahin?
No, I don't see any question. Yeah, thank you.
Okay, Vaughan, thank you so much for the wonderful talk and the interactions. I hope it will be seen by others who have not been present as well. So
Great.
thank you very much, and we appreciate this interaction very much. And so shall we then stop now?
Yeah.
Thank you. Yeah, it's been a pleasure talking, and thank you for the many ideas from all the questions.
Thank you so much.
Okay.
Thank you. Bye.
Bye for now.
Thank you, Padmakar, for helping us.
Thank you. Bye.